This is tutorial video 8 of the EDEXCEL P3 revision tutorial series. Today we will be looking at the types of radiation. We will be looking back over alpha, beta and gamma that we covered in episode 1 of these tutorial videos. We will also look at neutron radiation and positron radiation. We will be looking at the properties of alpha, beta, gamma, positron and neutron radiation. We will look at the process of beta decay, and we will use data to balance nuclear equations. Before we look at radiation, we need to remind ourselves of the structure of the atom. So the structure of the atom, which you should remember from year 10, all atoms have a neutral charge overall as they have the same number of electrons and protons. We have electrons on the outside in shells, which have a negative charge and a mass of nearly nothing. Inside the nucleus of the atom, we have two subatomic particles. We have the proton and the neutron. The protons have a positive charge of +1 and have the mass of 1. Neutrons have this same mass but are neutral, so have no charge. Overall, this helium atom would have a +2 charge in the nucleus and a -2 charge from the electrons, giving it an overall charge of 0, a neutral charge. So protons and neutrons have a relative mass of 1, electrons a relative mass of 0, and we have the respective relative charges. On the periodic table, all elements are displayed in this form, where we have the symbol, in this case He for helium. We have the mass number at the top, which is the number of protons plus the number of neutrons, and we have the proton or atomic number, which is the number of protons. And if we think back to episode 1 of these revision tutorials, we looked at the idea of ionization, which was where an atom turned into an ion due to radiation knocking off one of these electrons, turning it from a neutrally charged atom into a positively charged ion. And it was this ionization which was going to cause the danger. We will now look at the different types of radiation. So to begin with, we will look over the types of radiation. Our first type of radiation is our alpha radiation, where an unstable nucleus decays to become a new nucleus and gives off this alpha particle. The alpha particle is made up of 2 neutrons and 2 protons and can be thought of as a helium atom without the electrons. Our second type of radiation was our beta radiation. In beta radiation, a neutron decays to become a proton and an electron. So an unstable nucleus becomes a stable nucleus, gives off this beta particle, which is a high energy electron. The final form of radiation we looked at previously was our gamma radiation. Gamma radiation takes the form of a wave and is released whenever alpha radiation or beta radiation takes place. We've got our alpha particle here. The gamma radiation takes the form of this high energy wave. In the first revision tutorial, we mentioned that there was a second form of beta radiation known as positron emission. This is what we will look at now. So the type of beta decay that we have looked at involves the release of a high energy electron. However, there are 2 types of beta decay. The one we have looked at, which is known as beta minus, the minus coming from the charge of the electron. However, it is possible for this to have a positive charge. This is where the positron comes in. This new form of radioactive decay is known as beta plus decay and sees a proton turn into a neutron and release a positron. This positron is our beta plus particle and is the antiparticle of the electron. This means that it has the same energy and the same mass, but the opposite charge. To compare beta plus and beta minus, we can look at the following diagram. This diagram shows us both beta minus and beta plus decay. In beta minus, we have our carbon-14 becoming nitrogen-14, with one of the neutrons becoming a proton, releasing an antineutrino, and importantly, our high energy electron, our beta minus particle. This is opposite to our beta plus decay, where this time we have carbon-10 becoming boron-10, with one of the protons becoming a neutron, release of a neutrino, and a release of the positron. We can see its positive charge here. So in summary, in beta minus decay we have a neutron becoming a proton and releasing this electron, whereas in beta plus decay we have a proton becoming a neutron and releasing a positron. These are easier to remember if we look at the charges. So in beta minus decay we emit an electron which has a negative charge. In beta plus decay we release a positron which has a positive charge, a plus charge. The overall charge of these equations also remains equal, as we have a neutron, a charge of 0, becoming +1 plus -1, or 0 overall, and we have a charge of +1 becoming a neutral charge plus a positive charge, so we have a positive 1 charge here as well. The final form of radiation we're going to look at is neutron radiation. Neutron radiation happens when free neutrons hit stable atoms and make them unstable. In this way, it can be seen as a form of indirect radiation, as the unstable nucleus will then go through alpha or beta decay. These free neutrons are usually produced during a nuclear fission or nuclear fusion event. For a recap of nuclear fission and nuclear fusion, please watch the EDEXCEL P2 revision tutorial on this topic. So, as we can see, we have our free neutron which hits our target nucleus. This is going to cause it to break down, go through alpha decay or beta decay and release gamma rays. In this way, neutron radiation can be seen as the most ionizing. However, the initial neutron is not ionizing. They are, however, the most penetrating of all of the radiation types. And as you can see, this can, for example, in a nuclear fission chain reaction, cause multiple breakdowns to happen across multiple nuclei. We are now going to compare these 5 types of radiation. So for alpha, it has a charge of +2 and a mass of 4. It has a very low penetration ability and is stopped by paper, and has a very low range in air of just a few centimeters. It is made up of 2 neutrons and 2 protons, so it is a helium nucleus. However, it has very high ionizing ability, which makes it very dangerous if consumed, as it would be unable to get out of the body. Beta radiation, this is beta minus radiation, has a charge of -1 and a mass of 0. The mass of the electron is roughly 1/1800. It has a medium penetration ability and is stopped by aluminium. It has a larger range in air than alpha, now up to tens of centimeters. and is a high energy electron. Its ionizing ability is medium in that it is lower than alpha but higher than gamma. Gamma has a charge of 0 and a mass of 0 as it is a high energy wave. Its penetrative ability is very high, now stopped by lead, and has a very high range in air of many meters. It is a high energy wave that is part of the EM spectrum, but it has very low ionizing ability. Our positron radiation, or beta plus radiation, is the same as the beta minus radiation, except that it has a charge of +1. Its mass is 0 or 1 over 1800. Its penetrative ability is medium, as is its range in air. It is a positron, which is the antiparticle of the electron, or a positive electron, and it has medium ionizing ability. Finally, we have our neutron radiation, which has a charge of 0 and a mass of 1. It has very high penetrative ability, this time being stopped by thick concrete, and has very high range in air of many meters. It is a free neutron that has come from a nuclear fission or fusion event, and it has very high ionizing ability. However, this is indirect. The ionizing ability of the neutron itself is 0. We will now look at how to balance equations for these nuclear breakdowns. So first of all, we have our alpha decay, which is going to be giving off our alpha particle here, which has a mass of 4 and a proton number of 2. We have our americium-241, which is going to decay to our neptunium-237. This is a change of 4 in mass number. We also get this change in element because of this change in 2 of the atomic number. For beta minus decay, we now have strontium-90 decaying to yttrium-90 and giving off our high energy electron, our electron with a mass number of 0 and an atomic number of -1. This means that there has been no change in the overall mass number. However, because a neutron has become a proton, as we saw earlier, we have gained this 1 in atomic number. An easy way to calculate this, we have 39 minus 1 equals 38. Finally, for our beta plus decay, we now have carbon-11 decaying to boron-11 and giving off our positron. Our positron, also given the symbol E, again has a mass of 0, however this time has a charge of +1. So there has been no change in the overall mass number, just as we saw in beta minus decay. However, this time a proton has become a neutron, and so the overall proton number has gone down. An easy way to work this out, we have a proton number of 5, we're adding our 1 positron, and we get our proton number of 6. We will now look at 2 example questions for alpha decay. We will look at both beta minus decay and beta plus decay in more detail in the next tutorial video. This is our first example question for alpha decay. We are given our first element here, which is radium-226, and we are told that it's going to go through alpha decay. In the P3 exam, you will not be expected to work out the name of the new element, purely the number of neutrons and protons. Because this is alpha decay, we know that the mass number will have to decrease by 4, giving our new atom a mass number of 222. Likewise, our proton number will go down by 2, giving our new element a proton number of 86. When we look at the periodic table for element number 86, we find radon, which is given the symbol Rn. Here is a second example of alpha decay. Here we have tungsten 180 going through alpha decay. I want you to pause the video and work out the atomic mass, the atomic number, and the name and symbol of the new element. Your new element should have a mass number of 176, 180 take away 4, and a proton number of 72, 74 minus 2. Using the periodic table to look up element number 72, we can find that it is hafnium, given here by the symbol HF. We will look at beta plus and beta minus decay more in the next tutorial video, where we'll be focusing on stability graphs and quarks.